Welcome everybody to the Astromeeting seminar. The speaker today is Erika Korb from the University of Padova, where she's a student, and she's visiting Naples because she's the winner of the Coppola Prize for her master thesis. And today she will talk about black hole binaries. So please, anyone.
Thank you. Hello, everyone, and thank you for the presentation. Yes, I'm here because I won the Giuseppina Coppola Prize for my master thesis work, so I will start talking about that. And my master thesis investigated the role of Wolf-Rayet black hole binaries as the progenitors of the binary black holes that we observe with the gravitational waves to emit by gravitational wave. And I focused on trying to answering to this question: could this kind of system be the progenitors of the binary black holes? And spoiler, I found that yes, they are, and they are quite important kind of progenitor. Therefore, then I continued my work of the thesis in my first year of PhD, and I extended the analysis not only to exploring the progenitors of binary black holes, but also progenitors of all the compact objects that we observed to merge by gravitational wave emission. So also binary neutron stars and the black hole neutron stars. So I kind of tried to get a comprehensive view if, in general, a system composed by a Wolf-Rayet and a compact object, and well, by compact object in this presentation I will mean only neutron stars or black hole. I try to understand whether or not this kind of binaries could be the real important progenitors of the binary compact objects we have observed. And I found some interesting results with also some kind of agreement and hints with what you also observed today. So, first of all, a little bit of context. So far, you can see here that in a timeline of observations with the gravitational wave detectors, the number of observed binary black holes, binary neutron stars, and neutron star to merge with gravitational wave emission so far are about 100 of systems that are couples of black holes. Then there are 3 systems that we think are black hole neutron stars, and we also observed so far 2 neutron stars to merge by gravitational wave emission. So we have about 100 of these kind of binary compact objects that we have observed to merge, and we expect that this number grows and grows in the future with the updates to the feature detectors, the observagrams that are running now, the 04 observations, and also with the building of new detectors, maybe also the Einstein telescope that hopefully will be built in Italy, we hope. Otherwise, it will be somewhere in Europe. But the point is that we are observing a growing number of systems, and also with the ones that we have already observed, it is not so easy to understand where they come from. Because it is not so easy to understand where a binary of black holes, for instance, comes from in the first place. Because to form, for instance, 2 black holes or 2 neutron stars, the 2 initial stars that could be the progenitors need to undergo a lot of events and a lot of physics is involved between 2 main sequence stars and the formation of a binary compact object. The stars themselves, because of the stellar evolution, lose mass, evolve, change their radius, their properties, and this, of course, influences the mass of the remnant and the details of the stars as it is evolving. And this, the fact that, for instance, a star is bigger, less bigger, influences the fact that it could undergo mass transfer episodes. If a star is big enough to fill its Roche lobe, it can start to lose its mass, and its mass is then donated to the companion. So it is another star that changes its mass and its properties. And how does it happen? On which time scale does it happen? How mass is transferred? These are all details that are still under investigation. The models are still struggling to find a very detailed description of what's going on. especially if this kind of transfer becomes unstable and the star that is gaining mass just loses a lot of mass, and the core of the stars eventually are starting to rotate, for instance, in this blob of gas that was the envelope of the first star. This phase is called common envelope, and it could happen that the cores survive, the envelope is ejected, and the binary survives. Or it could be that the drag force is too high and the energy to remove the envelope is not enough, and then, for instance, the two stars could collide and merge prematurely, and the binary of black hole will never be formed, for instance. Also, other uncertainties in forming this kind of object could regard the fact that to form a compact object, we need a supernova explosion, a collapse, or an explosion with a further collapse. And the physics of supernova is complex, and this is still, again, not so well constrained. And there is not only the physics of the supernova that affects, for instance, the mass of the remnant, but also the fact that when a supernova explosion occurs, for the conservation of linear momentum, there is a kick in the compact object that is formed that could, for instance, break the binary, or if it does not break the binary, still it could change its orbital properties. So I did this to-do list just to get you an idea of how much physics is involved and how many processes, if not properly constrained, could affect what we are trying to find here. So what causes the formation of a binary black hole? And this is just what regards the formation of a binary black hole. If we want a binary black hole or a binary neutron star to also merge by gravitational wave emission, we need to take into account that a binary of objects that loses energy only by emitting gravitational waves requires a time to merge that follows this formula that was derived by Peters in 1964, that in general tells what we could expect. The more massive the objects, the easier it is for them to spiral in and merge. So a binary of black holes is easier, merges in less time than a binary of neutron star, for instance, starting from the same initial major axis. And the initial major axis actually is the thing that matter the most to have a binary of compact objects that merge, because the dependence is on the fourth power of the semi-major axis. So really, to have a binary compact object that merges, we need that the two compact objects are already close, but not too much close that the binary could not form in the first place. It's a delicate equilibrium. And then also you see that there is a dependence also on the eccentricity. This is not so much important in this work in this phase, but still it's something that we also need to account in our simulations and our description. And the point is that given that there is this delicate equilibrium in having a binary of compact object that forms, that is close but not too close, massive but not too massive. We eventually, if we, for instance, start to simulate a population of 100,000 binaries, we find that only one of them at solar metallicity could be a binary compact object that merges by gravitational wave emission within the lifetime of the universe. So that could be interesting for us to be detected with the gravitational wave detectors. So really, it's 1 over 100,000. It's a very low number. And the point is that to investigate what's going on, given that it's such a small number, and given that we need to be sure that what we find is not dependent on the assumptions of the models that we are taking into account, because they're not still very constrained, the best thing that we can do, and it is what I did in my thesis, is to carry on parameter exploration, see what happens in evolving a population of binaries under different assumptions, and do it in a quite fast way. And the best way to do this is to use a population synthesis code. In my thesis, I used the population synthesis code SEVN that was developed in the group I work in Padova. If other information are in the paper when it was released, and it is developed by Giuliano Iorio and collaborators in the group led by Michele Matelli, that was my supervisor. It is also my supervisor. The point is that this code carries on stellar evolution and binary evolution in a fast way, which means that it cannot solve the system of differential equation of the stars and carry on detailed evolution of each time step, because if we want to simulate a population and change the initial conditions, this would take ages. Instead, we need to evolve the properties of a star from a pre-computed grid. For instance, we use the grid of stars that were calculated in Padova from the parsec code. And we have these stars with their properties, and we add all the binary physics, mass transfer, supernova physics, tides, natal peaks, orbital evolution, and stuff with semi-analytic prescriptions, so basically fitting formulae. And by doing this, one binary is evolved just in a few seconds. So we did this, but evolving Milky Way-like populations. I evolved 5 million of binaries generated from initial conditions of masses, periods, eccentricities, following the distributions we observed of the Milky Way. And I did this work by changing 96 combinations of the parameter space. I explored 4 possible values for the metallicity, 2 for the solar metallicity, 2 for the subsolar metallicity, because metallicity affects the stellar winds physics. Also 2 values for the common envelope efficiency, that is, remember that case where the star could expand and the 2 stars were orbiting in this bubble of gas. That is the common envelope. The facility with which that envelope is ejected really affects our conclusions, so explore 2 values for that. Also explored 3 possible models for the collapse supernova that allow us to form different ranges of compact object masses, and also for models for the natal peaks that are stronger, less strong, to really understand what's going on. And what I found, and in all these simulations, I focused on trying to find whether or not the systems that merge have evolved through the phase of Wolf-Rayet black hole or Wolf-Rayet neutron star. Why? Why should this kind of systems be important to investigate? Because if we wanted to form a binary of black holes or neutron stars, having already a black hole or neutron star, of course, helps. And then the Wolf-Rayet star is a star that usually it is massive enough to form another black hole or neutron star. And that, given that a Wolf-Rayet star is a star that basically lacks its external envelope of hydrogen, is usually found having only a helium already surface or also carbon, it is possible that such a star could be formed after a mass transfer event. It could be that star that was stripped away. So having this kind of interaction helps to reduce the size of the orbit. So it could be an hint that that system then can be the one that merges. And the point is that from a theoretical point of view, these systems are very interesting, promising, but we have only observed 7 Wolf-Rayet black hole candidates so far, and we are still not sure they are Wolf-Rayet black hole, Wolf-Rayet neutron star, for instance, because from an observational point of view, it's really difficult to get the measurement of the mass. But still, for instance, we are approaching this from a theoretical point of view, then we will come back to the observational side. So I did my simulations, I investigated whether or not this binary of compact objects evolved from Wolf-Rayet compact object configuration, and the answer is yes. More than 99% of all the binary compact objects I found to merge by gravitational wave emission within the lifetime of the universe have indeed evolved at some point in their life as a Wolf-Rayet black hole or as a Wolf-Rayet neutron star. And this happened no matter the combination of the parameters I assumed. So it is reasonable to say that this happens even though we are not sure of the models because it happens anyway we combine the models, at least the ones I explored. And to let you be more convinced of this, this solidity, this is plotting with a lot of information. You can see here, for instance, for one of the values of the common envelope efficiency and for the solar metallicity value, all the combinations of supernova and natal peaks are lines, and you can see the fraction with the different colors, the fraction of, for instance, binary black hole that evolved as a Wolf-Rayet black hole over all the binary black holes that merge gravitational wave emission. And we find, for instance, that these crosses are always all of them. So all binary black holes evolved from Wolf-Rayet black holes. Similarly, all binary neutron stars evolved from Wolf-Rayet neutron stars, the yellow crosses. And then for the mixed type of binary compact objects, the ones with a black hole or a neutron star that could come either from a Wolf-Rayet black hole or from a Wolf-Rayet neutron star, I have these other two points, the pentagon and the cyan circle, and you see that the probability that a black hole neutron star merging by gravitational wave emission, evolved from one progenitor or another changes with our assumptions, but overall the sum of the two always sums to 1. It's just our relative weight, and we see that in general we favor the formation of through the Wolf-Rayet black hole channel, but overall, either as a Wolf-Rayet black hole or as a Wolf-Rayet neutron star, still that is the progenitor of a black hole neutron star merging. And this happens, for instance, for this kind of combination of parameters, the same plot, but for all the parameters I explored, all the metallicities, the two values of the common envelope efficiency in the rows, and basically you see that binary black holes, binary neutron stars always are at one value of the fraction of production, and the other evolutionary pathways, changing weight, for instance, for the relative weight, again for the black hole neutron star formation pathways, the metallicity mostly affects the relative weight, but still the fact that they all came from a Wolf-Rayet black hole or a Wolf-Rayet neutron star doesn't change nowhere in the parameter space explored. So, other graph. Here you see that indeed the possibility that a Wolf-Rayet or a Wolf-Rayet black hole or a Wolf-Rayet neutron star just by itself exists, no matter the fate it undergoes, is pretty high. Here, focus only on the two upper lines in these plots where you see for the two common envelope efficiency and all the 4 metallicities, the fraction of binaries of all the million of simulated binaries that evolved as a Wolf-Rayet black hole or a Wolf-Rayet neutron star. And you see that averaging this fraction over all the collapse supernova and peak models, there is always 10% of all the simulated binaries that evolves as a Wolf-Rayet black hole, and there is always 30% of all the simulated binaries that evolves as a Wolf-Rayet neutron star. So Wolf-Rayet neutron star, Wolf-Rayet black hole systems are quite common, we can say, to form, but it is very difficult that, and the information efficiency does not depend on the parameters, basically. But having this kind of objects and becoming a black hole, a binary compact object merging by gravitational wave emission is not so easy. Here you see, again, the fraction of binary black holes in purple, binary black hole neutron stars in cyan, and binary neutron star in yellow, of all the simulated binaries that are occurring for the different combination of parameters. And you see that, for instance, having a binary black hole in general is easy at low metallicity, less easy at solar metallicity, because stellar winds are very efficient in removing mass at high metallicity. Black holes are massive, so it's more difficult to form a black hole and a binary black hole if we have strong winds which occurs at high metallicity. Instead, forming a neutron star, for instance, is less dependent on the parameter space. But the point is that I wanted to make is that the probability that a Wolf-Rayet black hole and Wolf-Rayet neutron star is a progenitor of the binary compact objects is kind of true. Let's say that that is the progenitor, but it is not true the contrary. Very few of this kind of system, even though they are efficiently formed, very few of them will become a binary neutron star, a binary black hole, and this production efficiency depends on the parameters that we are considering, on the metallicity, on the common envelope efficiency, and really less than 10% has this kind of fate. Why? Let's try to see why. Here you see a grid similar to before, just for one common envelope efficiency. There are the different metallicities. There are all the models of perhaps supernova and big models. And here you see the possible fates of Wolf-Rayet black holes in the first row and the possible fates of a Wolf-Rayet neutron star, always expressed in terms of fraction. So the possibility that, for instance, a Wolf-Rayet black hole does form a binary black hole, broken and not broken, or not a binary black hole that is the dashed line. Similarly, a Wolf-Rayet neutron star, we have all these kind of fates in the legend here. And there are a lot of information, I'm aware of it. I want you to focus on this kind of lines, the merger ones. Basically, the darker shades are almost non-visible in this kind of plot, because the probability that this kind of Wolf-Rayet black hole or Wolf-Rayet neutron star has a fate of merging binary black hole, neutron star, whatever, is ridiculously low. It is only appreciable, for instance, for binary black holes forming at low metallicity, because at low metallicity we are very good at forming binary black holes. But in general, Wolf-Rayet black hole systems prefer to just remain a binary black hole, not merging, or a broken one, while Wolf-Rayet neutron stars are very good at colliding with themselves, not surviving as a binary compact object. And for instance, the Wolf-Rayet can also become a dwarf rather than another neutron star. Or if it survives as a neutron star systems, they are very good at breaking themselves. And the point is that, for instance, at low common envelope efficiency, the survival probability of binary neutron stars is really, really low. And this happens because, in general, the formation channels of this kind of objects are quite easy to describe, in the sense that to have a binary compact object that merges, we require at least one mass transfer event prior to the formation of Wolf-Rayet compact object systems. And the good thing is that while Wolf-Rayet black holes, once they are formed after a mass transfer event, do not undergo other mass transfer events, Wolf-Rayet neutron stars require another mass transfer event to shrink their orbit, because they are not so massive to merge by gravitational wave emission unless their orbit is further reduced. But if we do this initial mass transfer at low common envelope efficiency, we are saying that we are not using a lot of energy to eject the envelope, and our stars are still orbiting in this bubble of gas. There is too much drag force, and the two stars will not be able to eject the drag force efficiently. So eventually they will spiral down and collide, and the binary will not be formed. That's why, for instance, binary neutron stars at low metallicity that are already difficult to form, and at low common envelope efficiency, for instance, are basically very, very difficult to form through Wolf-Rayet neutron stars, even though all the ones that form have this kind of pathway. And okay, so here is just a recap of what I said. So Wolf-Rayet black hole, Wolf-Rayet neutron stars are the key progenitors to the binary compact objects that merge in gravitational wave emission, but it is not so common that this is the fate of Wolf-Rayet compact objects. They rather have a different history, evolutionary history. And this was all the theoretical stuff of my work. Let's see if this is in agreement with what we know or is it not. So this is the last thing I'm exploring for now. So starting from that's why there is this preliminary. We said that, for instance, all binary black holes evolve from a Wolf-Rayet black hole. So if we assume, for instance, a model that is able to predict the spin of the secondary black hole forming from the Wolf-Rayet, and we adopt this model, for instance, that assumes that the spin of the black hole that is born from the Wolf-Rayet depends, its magnitude depends only on the period and on the mass of the progenitor, because it assumes that it is spin up only by types, basically. So either the orbit is closed or there is no spin up. We should expect to see, for instance, a bimodal distribution for all the metallicities, for all the combination of parameters I explored. We expect basically that either the binary is tight enough to produce a spin up, or the black hole is not spinning because the binary was too much larger. Is this in agreement with what we derived from gravitational wave observations? No, not at all. Gravitational wave observations are able to give us a way to derive, and indirectly, but still derive the spin of the black holes. And we see that the distribution is expected to peak for black holes that are spinning but not so fast. And the fact that these distributions are so in disagreement could hint us, for instance, that this model maybe is too simple to describe what we know about the information. That if it's true, and it appears to be reasonable, that all Wolf-Rayet black holes, that all black holes come from Wolf-Rayet black holes, while having this kind of system could be, this kind of model could be too much simple to describe the physics that is going on. From another point of view, it could be that maybe this is correct, but maybe all the binary black holes we observe evolving in this way from isolated channel are not so abundant. There are also other possibility to form a binary black holes by dynamical assembly. So maybe this kind of revolution, it is correct, but it is not the major one. Open questions to be investigated. Let's go to another possible constraint for the observations. I talked to, before I said to you, there are only 7 Wolf-Rayet black hole candidates known so far. These are the candidates, and you see that most of them have the masses not so well constrained. And the only one in the Milky Way is Cyg X-3. So it could be a really good idea to try to see if we are able, for instance, to reproduce the properties of this kind of Wolf-Rayet black hole binaries. And yes, we are. We find some systems that exhibit these properties, but you see, this is one of the first plots I showed you, the abundance of Wolf-Rayet black hole or Wolf-Rayet neutron stars in all the binaries simulated for the parameter space considered. And you see that while Wolf-Rayet black hole and Wolf-Rayet neutron star are quite abundant, Wolf-Rayet black hole or Wolf-Rayet neutron star with the properties of Cyg X-3 are very rare. Lower, at least 1 order of magnitude, if not 3 orders of magnitude rarer than a general Wolf-Rayet neutron star or a general Wolf-Rayet black hole. The formation of this kind of Cyg X-3 like binaries depends on the metallicity, but still we should focus on the formation at solar metallicity because Cyg X-3 is in our Milky Way. So let's try to see what could be the fate of Cyg X-3. We said before that all of Wolf-Rayet compact objects we barely form a binary compact object merging less than 3% of them. Well, Cyg X-3 from this point of view, even though it's difficult to form, he also is not so probable it will form a merging binary compact object. But there is a trick. I'm considering all Cygnus X-3 candidates, and you saw here that in general we are able to form much more efficiently Wolf-Rayet neutron star than Wolf-Rayet black holes. And the trick is that Wolf-Rayet neutron stars will not merge. Less than 1% of them will not merge. But Wolf-Rayet black holes with the characteristics of Cygnus X-3 are much more probable to merge. It depends, of course, on the parameters we are considering. But less than 70% of, at most 70% of Cygnus X-3 from the solar metallicity could have this kind of fate of merging binary. And the point is that Cygnus X-3, so on one hand, it is likely to be a Wolf-Rayet neutron star from a theoretical point of view. And if it is a Wolf-Rayet neutron star, it will not merge. But if it is a Wolf-Rayet black hole, then it is almost certain that if it is survives as a binary, it will be a binary that merges by gravitational wave emission. Because if we go back and compare to the general probable fate of a Wolf-Rayet black hole, we see that the darkest shades of being a merging binary compact object are much more probable for a Wolf-Rayet black hole binary with the configurations of Cygnus X-3 with respect to a general Wolf-Rayet black hole binary. And we can be more convinced of this. This is, I promise you, the last complicated plot I showed you. Here there are the orbital properties of Wolf-Rayet compact objects that will produce a merging binary black hole, binary neutron star. Here you see the semi-major axis and the total binary mass for instance, one envelope efficiency and a solar metallicity value at the beginning of the Wolf-Rayet compact object phase and the end of the Wolf-Rayet compact object phase. The different colors indicate different possible fates. So, for instance, in yellow we see Wolf-Rayet neutron stars that will become binary neutron stars. In purple, Wolf-Rayet black holes becoming binary black holes, etc. And we see that there is these properties of space, and binaries with the properties of Cygnus X-3 should fall only in this small window. And if we plot when the binaries have the properties of Cygnus X-3, we find that Cygnus X-3-like binaries occur only at the latest stages of the Wolf-Rayet compact object phase. So a binary like Cygnus X-3 is really towards the end of its evolution, just prior to the formation of the binary compact object. That is why it is much more probable that if it is a Wolf-Rayet black hole, it will become much more probably a binary black hole merging by gravitational wave emission. And I just want to show you that instead, if Cygnus X-3 is a Wolf-Rayet neutron star, Wolf-Rayet neutron star, given that they undergo that additional mass transfer event, the Cygnus X-3 phase, they start well far away from the Cygnus X-3 window, let's say. They evolve, they do that one additional mass transfer, so they just cross in that moment the Cygnus X-3 configuration, and then they end up with having a much smaller semi-major axis. That's why it is very rare that and very difficult that they are able to become merging binary neutron stars, because just little differences in that mass transfer event and the black hole neutron stars are not here. They just do not exist. The two objects collided before. So this is just a recap for the information, so there are a lot. So I try to understand whether or not binary compact objects merging by gravitational wave emission could have evolved from a Wolf-Rayet compact object configuration, and I try to answer to this question by doing a parameter exploration with a population synthesis code. The answer was yes, they are the key progenitors to form this kind of objects, but it is rare that they form that kind of object. So all black hole neutron stars binary neutron stars, binary black holes, emerging gravitational wave emission evolved in this way, but it is not a common pathway. It is very rare. We need too much things to go in the right place to form this kind of objects. And this depends mainly on the metallicity, for instance, on the type of object that we are forming. We have also kind of, this can allow us to put observational constraints or to better understand what we observe from gravitational waves, for instance, the information on the spin of the secondary black hole. And also, we saw that observing binaries like Cyg X-3, that if they are Wolf-Rayet black holes, could be really one of these progenitors, could help us to understand more what's going on. So observation could really help to understand and better constrain all these kind of models, and maybe in the future avoid us to do all the time this kind of parameter exploration. And that's all. Thank you for your attention.
Questions or comments?